Weather prediction is one of modern science's most impressive achievements. Meteorology relies on equations such as the Navier-Stokes equations and ideal gas laws. These describe the relationships between atmospheric variables, temperature, wind speed, density, pressure, and so on both static and variable scopes. However, weather is chaotic, and small changes in initial conditions can lead to wildly different outcomes, a phenomenon known as the butterfly effect. In 1922, Louis Fry Richardson attempted to forecast weather using these equations, but his methods were so slow it would have taken a week to predict tomorrow's weather. Today, numerical weather prediction uses computers to discretize these equations, solving them iteratively across grids that average atmospheric variables over specific areas. While this enables dramatically faster and more accurate predictions, we still face limitations predicting processes like rain formation, as it happens on a much smaller scale than models typically resolve. However, AI, such as generative adversarial networks, has had recent success in predicting precipitation over the UK. A GAN is a pair of machine learning models where one acts like an artist and another a seasoned critic. The artist tries to convincingly imitate pieces, while the critic has to tell whether or not its paintings are authentic. As they compete, the artist takes criticism to improve their skills, while the critic gets better at spotting the differences. In this analogy, the generator model is the artist and the discriminator is the critic. They are in a training loop where the discriminator evaluates real and generated data, while the generator tries to create data that fools the discriminator. Every time the discriminator identifies fake data, the generator's parameters improve. When the discriminator guesses wrong, its parameters improve. The math behind GANs revolves around an objective value function, which represents the competition between the generator and the discriminator. The discriminator evaluates d of g of z, the probability that the generated data is real, and minimizes it by adjusting its parameters using gradient descent, a method rooted in optimization and stochastic calculus. This ensures it better distinguishes real from fake data, dynamically improving its classification accuracy. Opposingly, the generator aims to maximize d of g of z by making the data as realistic as possible. This adversarial interplay allows for dynamic optimization. In meteorology, GANs are used for resolution upscaling. Think of a blurry weather map as low quality input data. The generator learns to transform that blurry map into a high resolution one. The discriminator then compares the accuracy of the new map against the existing data. Machine learning not only improves rainfall prediction, but also aids disaster preparedness by identifying likely outcomes of extreme weather. Yet, as powerful as AI has become, the chaotic nature of the atmosphere ensures that some uncertainty will always remain.